Hello everybody, welcome back to another Gregorius Maths video. In this video, Theorem of the Week, I'll be talking about the fundamental theorem of algebra. And, okay, yeah, so many of you probably heard of it. I am, again, going to be using degrees and homotopy and stuff to be proving it, just as I did in the last Theorem of the Week. So yeah, I might as well get on with it. So the statement actually, this has so many different proofs, but I'm going to obviously be choosing my favourite one, the one with homotopies and stuff. So let me just state the theorem, just so that I can have it on the board. Let me just state it, theorem. So what's the fundamental theorem of algebra say? It says any polynomial we'll call it f of z, where z is, with so we'll write it out, hold on, equal to z to the n plus c1 z to the n minus 1 plus up until c n minus 1. Any polynomial of this form, where Cn is, where each of these coefficients are complex numbers, has at least one root. Actually, technically I should say it has n roots if you take into account multiplicities, so that is kind of like repeated roots. However, if I show that this statement is true, then I can prove the other statement inductively by just considering the polynomial given by f of z divided by z minus c, where c is some root, and of course this will have another root, and so we can just do it inductively. So we'll just be proving this statement here. Now, firstly, we'll assume that for all x in the circle, so that is for all x such that the magnitude of x is equal to 1, we'll assume that f of x is not equal to 0. Now, this allows us to define f hat from the circle to the circle given by x maps to f of x divided by the magnitude of f of x. Okay, so we're going to compute the degree of f hat. So, let me just write this out more clearly. So firstly, what we're going to do is, let's assume that that f of x is not equal to 0 when x is less than or equal to 1. Then we can actually, we are within our rights to define another a homotopy h from S1 cross I to S1 given by x maps to f hat of xt. Sorry, I should say xt maps to double input, like so. And we're allowed to do this because we've assumed that there's no roots for x less than or equal to 1. And what we notice now is that because f is continuous, h is a homotopy. Let me write this in a different colour. H is a homotopy between the constant map f hat of 0 and f hat, because when t is equal to 1 we just get f hat. And because of course this is a constant map, we can therefore obtain that f hat, the degree, sorry, of f hat, degree of f hat is equal to 0. Now, so we've shown that if we assume that the polynomial has no roots for any magnitude of x less than or equal to 1, we've shown that the degree of this map is equal to 0. Now, what we're going to do, let me just say, now assume, actually let me do it in Greek. Now assume that f of x is not equal to 0 for x greater than or equal to 1. Sorry, the magnitude of x greater than or equal to 1. Then we can define another map. We can define a map, we'll call it J, from S1 cross I to S1. And what does J do? J will map xt will map to k of xt divided by the absolute value of k of xt. Now, what's k? K k of xt is equal to t to the n times f of x over t. So that is equal to, because now you're going to say, oh well, t could be equal to 0, blah blah blah. That is equal to x to the n plus t times c1 x to the n minus 1 plus t times c2 x to the n minus 2 plus up until t to the should I say n minus 2 c n minus 1, like so. So this is really, this is just shorthand for this. Now, okay. So why is it, so it's allowing us to okay, and so our map J is really, what is it doing? Well, it's doing t to the n over the magnitude of t to the n times f of x over t divided by the magnitude of f of x over t, which is just f hat of x over t. And so this is why we need the assumption that there are no roots for the magnitude of x greater than or equal to 1. Now, yeah, I believe actually because t is between 0 and 1, we can just cancel this part out. So that's good. But I'm not going to do that. I don't think that's really necessary, because all we need to know is that this defines another homotopy. So what does this homotopy do? Well, J defines a homotopy between, well, when t is equal to 0, this part vanishes, so we're just left with x to the n. So we'll call that Fn, because I think that's how it's, well, I think it's actually denoted by omega actually, I think normally. So we'll have omega n, which is just going around the circle n times, is homotopic too. Well, when t is equal to 1, we just plug it in here, t is equal to 1, we just get f hat. However, we know that this loop going around n times, its winding number is n. So like we could just say its degree is n. So we have that the degree of f hat is equal to n. But earlier we showed that the degree is equal to 0. And therefore, the only time when this is true, sorry, this is not true, is when the degree of the polynomial is 0. That is, it's just a constant, which is obvious, right? So, therefore, if n is not equal to 0, then of course one of these assumptions must have been false, and therefore it must have a root, at least one root. And of course, once we have one root, we can get n. We can extrapolate n roots from it, or accounting for multiplicities. So what did we do? We cleverly constructed. We cleverly constructed various different homotopies, using different assumptions, in order to obtain something contradictory, and we again utilized degree theory. I think this is just a really simple proof, and it's extremely surprising if you told me, like, fundamental theorem of algebra can be proved using homotopy. I'd probably find you crazy, but here it is. So yeah, it just goes to show the power, the interconnectedness, all of that deep stuff. And it's just, one of those theorems, which is classic. It's a classic. So yeah, hopefully you enjoyed Theorem of the Week, and hopefully I'll be back soon. So yeah, goodbye. Also, before I go, I got this proof from J.P. May, his Concise Course in Algebraic Topology, which is a very good book. I would recommend. I just thought I'd point that out. So yeah, good day.